Hello, welcome to another module in this massive open online course. So, we are looking, we have looked at the Hilbert transform, correct, and also the impulse response of the Hilbert transformer and the spectrum, that is the Fourier transform of the Hilbert transformer. Now, let us look at the application, that is let us look at the generation of the SSB signal, that is a single sideband modulated signal using the Hilbert transform, alright. So, today let us look at SSB generation using the Hilbert transformer or the phase shifting method, which is based on the Hilbert transform. Based on the phase shifting method. Okay. And as we have already said, the phase shifting method, this employs the Hilbert transform. Now, for this purpose, consider the message signal MT, alright, with spectrum MF. Okay. So, to illustrate single sideband modulation, consider MT with spectrum MF, all right. Let us draw this spectrum. Let this spectrum be represented as follows. This is your MF, okay. Maximum frequency is FM minus FM. Now, what we will denote is we will write these numbers 1 to indicate that this is the original baseband spectrum with the positive frequency band and the negative frequency band scaled by unity, alright. So, this is simply the original message spectrum. Just to keep track of the various scaling factors, we are going to start with the original message spectrum, denote that this message spectrum, both the side bands, right, the positive side band and the positive band, that is comprising of the frequency components, the positive frequencies and the negative frequencies are scaled by unity, alright. So, this is your positive frequency band and this is similarly the negative frequency band, and both of these are scaled by unity. Scaled by unity means the original scaled by unity implies that they are essentially they are essentially the original message spectrum, alright. Now, let us consider the following signal xt given as, consider rather the modulated signal xt consider the modulated signal xt given as xt equals mt cosine 2 pi fct minus m hat t sine 2 pi fct, correct, where m hat of t, we already know this, m hat of t is the Hilbert transform. is the Hilbert transform m hat of t is the Hilbert transform of the signal mt, and x t is mt cosine 2 pi f c t minus m hat t sine 2 pi f c t. Let f c is the carrier frequency, we already know that. M hat t is the Hilbert transform of mt, and we will show that this x t is in fact a single sideband modulated signal. So, what we are going to show is that this x t will show that x t is in fact your SSB signal. So, we will in fact show that x t is the SSB signal. So, what we are doing, given a message signal m t, we are using m t and also using m hat t, which is the Hilbert transform of m t or the phase shifted version of m t to generate the single sideband modulated signal. Therefore, this is termed as the phase shifting method for the generation of a single sideband modulated signal. So, basically since we are using m t and the phase shifted signal, and the phase shifted signal m hat of t, this is termed as the phase shifting method. Phase shifting method for generation of the phase shifting method for generation of the SSB signal. Now, let us consider this component by component. Let us look at mt cosine 2 pi f c t. We have already seen this is simply your double sideband suppressed carrier signal which has spectrum, which is given as the spectrum. So, let us look at the spectrum of this, that is equivalently we already know that is given as half m f minus f c, that is and plus half m f plus f c, that is spectrum m f shifted to f c scaled by half, spectrum m f shifted to minus f c scaled by half. So, each of the sidebands are scaled by half. Okay. So, if I draw this, it is going to look like at f c I am going to have minus f m and each of the sidebands is scaled by half, correct. So, this is at minus f c, and what I have is from this is f c. So, this is f c plus f m, f c minus f m minus f c plus f m minus f c minus f m, and again each of these bands are scaled by half. This is your, the right side is your m f minus f c, the left side is your m f plus f c. We have already seen this, correct. So, what we have is that the baseband spectrum of m t, that is m f, is shifted to f c scaled by half, shifted to minus f c scaled by half. What is more interesting is the spectrum of m hat t times sine 2 pi f c t. So, let us look at that, that is your, now let us look at this m hat t sine 2 pi f c t. Now, first for this let us look at the spectrum of m hat of t, that is let m hat of t have the spectrum, that is a Hilbert transform of m t have the spectrum m hat of f. Then we know that m hat of f is nothing but, we have seen this in the properties of the Hilbert transform, is the spectrum MF multiplied by the Fourier transform of the Hilbert transformer, which is minus j sin f. So, therefore, what you have, this is MF original spectrum MF, this is multiplied by minus j sin f, which means that the positive frequency side is multiplied by the scaling factor minus j, negative frequency side is multiplied by the scaling factor. This is, remember, positive frequency scaled by minus j, or phase shifted by minus pi by 2. This is your negative frequency band scaled by j, alright, because the Hilbert transform, remember this Fourier transform, the spectrum of the Hilbert transform is given by minus j sin f, which means basically all the positive frequency components of the input signal are multiplied by minus j, the negative frequency components are multiplied by j. At 0 it is multiplied precisely by 0, but we are going to ignore that one point where it is multiplied by 0, because that it can be shown that that does not have a signal, that does not lead to so that does not lead to any significant, any perceivable difference in the rest of the processing, right, because that is a single point. At that single point 0, it is exactly 0, it is slightly cumbersome to draw that over here. So, we will ignore that and we will simply say that the positive frequency band is scaled by minus j, the negative frequency band is scaled by j. So, this is the spectrum m hat of f, the spectrum of m hat of f. Now, m hat of t sin 2 pi f c t that is modulated by the sine wave, that is m hat of t, sine can be represented as e to the power of j 2 pi f c t minus e to the power of minus j 2 pi f c t divided by 2 j, alright. I can equivalently write the sine 2 pi f c t as e to the power of j 2 pi f c t minus e to the power of minus j 2 pi f c t divided by 2 j, and therefore, now this is basically separating this, this is m hat of t e to the power of j 2 pi f c t by 2 j minus m hat of t e to the power of minus j 2 pi f c t divided by 2 j. And now, if I take the spectrum of this is, well, m hat of e to the power multiplying by e to the power of j 2 pi f c t using the modulation property, that is m hat f minus f c divided by 2 j minus multiplying by e to the power of minus j 2 pi f c t, that is modulation property shifting to minus f c m hat of f plus f c divided by 2 j, which is basically nothing but minus j over 2 m hat f minus f c plus j over 2 m hat f plus f c. And what is this? And this you can see basically is the spectrum, this is the spectrum, this is the spectrum of m hat of t sin 2 pi f c t. So, it has m hat shifted to f c, that is m hat f minus f c multiplied by minus j by 2, and m hat f plus f c that is shifted to minus f c and multiplied by j by 2. And therefore, now we will have, if you look at this, this is the spectrum of m hat of f, that is positive band scaled by minus j, negative band scaled by j. So, therefore, what we are going to do is now, remember, shift this to f c. We already have positive band scaled by j, positive band scaled by minus j, negative band scaled by j. shift this to minus f c, and we are going to have again j minus f c. Now, this has to be multiplied by j over 2, or rather this has to be multiplied by minus j over 2, and this has to be multiplied by j over 2. Remember, you have to shift it to f c multiply by minus j over 2, shift it to minus f c multiply by j over 2. Therefore, the net resulting spectrum is given as something like this. The net resulting spectrum, will be, well, at f c you will have minus j multiplied by minus j by 2. So, that gives positive band multiplied by minus half, j multiplied by minus j by 2 multiplied by this scaling factor is half. This is at f c. At minus f c we will have something interesting. J minus j multiplied by j by 2. So, that will give us the lower band. This is multiplied by half, j multiplied by j by 2, upper band multiplied by minus half, and therefore, this is now the spectrum. Now, this is basically your spectrum of m hat of t sin 2 pi f c t. And now, you can see the various scaling factors. Some of the scaling factors are half, some of the scaling factors are minus half. This is a spectrum of m hat t sin 2 pi f c t. For this, first we have derived the spectrum of m hat t, which is m hat f, which is m f minus j sin f, plus the modulation effect with respect to sin 2 pi f c t, that is shifting to f c multiplying by minus j by 2, shifting to minus f c multiplying by j by 2, and that gives us this final spectrum. Now, the spectrum of m t cosine 2 pi f c t minus m hat t sin 2 pi f c t is the subtraction of the two spectra that are derived above. That is the spectra for, remember, this is the spectra of m t, this is a spectra of m t of m t cosine 2 pi f c t. Let us call this spectra 1. Okay. This is a spectra of m hat t sin 2 pi f c t. Let us call this spectra 2, or the second spectrum. Now, the spectrum of x t equals m t cosine 2 pi f c t minus m hat t sin 2 pi f c t. This spectrum is equal to spectra of 1, that is m t cosine minus 2 pi f c t minus spectra 2, that is spectrum of, and that now if you look at, so now look at this, if look at this, in this the upper side band, if you look at this spectrum, the upper side band is scaled by half, lower side band is scaled by half. here the upper sideband in m hat t sin 2 pi f c t, upper sideband is scaled by minus half, lower sideband is scaled by half. Therefore, if you subtract spectra 2 from spectra 1, the upper sidebands will add, half plus half, the lower sidebands will cancel, half minus half. Therefore, what remains is the upper sideband modulated signal, and that will be given something like this. The upper side spectra 1 minus spectra 2, that will be given as the upper side bands, the factors of half and half will add, that will give a scaling factor of 1 for the upper side band, scaling factor of 0 for the lower side band, and therefore, what we will have is basically, now if you look at this, the net signal that you will get will be something like, okay. So, this is f c, this is minus f c, this is the USB spectrum or spectrum of the USB signal. So, x t equals m t cosine 2 pi f c t minus m hat t psi 2 pi f c t. What we have shown that this is indeed the upper sideband modulated signal. This is indeed the upper sideband modulated signal, or basically the USB signal. Okay, this is indeed the upper sideband. Similarly, now it is not very difficult to show that the other signal, that is m t cosine 2 pi f c t plus m hat t sin 2 pi f c t, will be the lower sideband modulated signal, because when you add spectra 1 and spectra 2, the upper sidebands, which are scaling factors of half and minus half, will cancel, add to 0. The lower sideband, which has scaling factors of half and half, will add to give the scaling factor 1. Therefore, that will be the lower sideband modulated signal. So, the other signal x L t, let us call this, or let us call this x L t equals m t cosine 2 pi f c t plus m hat t, and spectrum of x L t is equal to spectra 1 plus spectra 2, and if you do that, you will notice that only the lower side bands, only the lower side band, this is f c, the lower side band, only the lower side band will survive, and what you have is, this is basically spectrum of the LSB signal. So, this is the spectrum of the LSB signal. So, basically to summarize, what we have shown is that the USB signal, upper sideband modulated signal, is m t cosine 2 pi f c t minus m hat t sin 2 pi f c t, and the lower sideband modulated signal is m t cosine 2 pi f c t plus m hat of t sine 2 pi f c of t, and since this employs the phase shifting, the phase shifter, that is a Hilbert transformer to generate m hat of t, this is basically based on the phase shift, this is basically the phase shifting method to generate a single sideband modulated signal. And therefore, we have seen now without the use of any low pass or high pass filters, remember that was the disadvantage of the frequency discrimination technique, because we needed low pass and high pass filters with very sharp cutoffs, alright, very sharp cutoffs in the sense that the pass band and the stop band, but no transition band. If there is a transition band, that leads to basically picking up of some vestiges, right, which are unwanted portions of the signal. Therefore, and it is very complex to design such filters with very sharp cutoffs, and therefore, this is an alternative technique which does not use such filters with such sharp cutoffs, but is based on the phase shifting, based on the phase shifter, or rather the Hilbert transformer to generate single sideband modulated signal can be used to generate both the upper sideband and lower sideband modulated signals by modulating mt and cosine 2 pi f c t, and the Hilbert transform of mt, that is m hat of t on sine 2 pi f c t. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.